Hi everyone, my name is Andrew Loveless. I'm a PhD student at the University of Michigan and an engineer at NASA Johnson Space Center. And today I'm going to talk to you about IGOR, which is our new approach for building Byzantine fault-tolerant embedded systems with very low latency. This was work I completed with my advisors Ronald and Baris, and also with Linh Phan at the University of Pennsylvania. One very common requirement in the design of embedded systems is to tolerate faults. And typically the types of faults a system needs to tolerate depends on the consequence of faults not being mitigated. So for example, a fault in a robot in a manufacturing plant could result in some reduced production capacity, but it's not life-threatening, so it may not be worth the added cost of tolerating every type of fault. On the other hand, a fault in a commercial aircraft can have really serious consequences, so loss of life, millions of dollars in damage. So as a result, it's necessary to design the system to tolerate any fault that's remotely credible. Specifically, the fault tolerance needed in safety-critical systems like aircraft and spacecraft is called Byzantine fault tolerance. This means that the system is designed to work even if devices fail in the worst way possible. So for example, a faulty computer could send conflicting malicious commands to different parts of the system. The standard way to design BFT systems is with state-machine replication, or SMR. The idea behind SMR is to have redundant copies of the sensors, actuators, and compute nodes, which we call replicas here, that all execute at the same time. That way, if some of these devices become faulty, the system can mask them and continue to operate correctly. SMR systems proceed in two phases. In the agreement phase, the replicas receive data from the sensors. However, since a sensor may be faulty, different replicas may get different data from the same sensor. To correct this, the replicas run an agreement protocol to agree on one common set of sensor data. Then, the replicas execute a source selection algorithm to select one trusted sensor value as the input for their computation. In the simplest case, source selection can just be a mid-value selection, which is what we show here. Next, we have the execution phase. In this phase, the replicas execute on the chosen sensor value and deliver results to the actuators. The actuators then vote the outputs that they receive in order to mask any faulty replicas. The problem with this agree then execute approach to SMR is that it results in high latency. In our paper, we show that it often results in latencies in BFT embedded systems that are actually double that of non-replicated systems. This means that it can become impossible to meet certain hard deadlines in safety-critical applications. Also, even in cases where you can meet deadlines, that higher latency inevitably causes a drop in control performance, which the software then has to compensate for. One common way to reduce the latency of BFT in non-real-time systems, like in data centers, is to use speculation. The idea here is to skip agreement altogether and assume the replicas will select the same sensor values for their computation. This makes speculative systems very fast in the fault-free case, where replicas naturally agree with each other. However, if a sensor is faulty, it can cause the replicas to get different inputs, their states to diverge, and the vote at the actuators to fail, in which case the system needs to roll back and re-execute the request, which requires them to run an agreement protocol. So this means that in the worst case, where faults occur, speculative systems are at least as slow as non-speculative systems, and oftentimes they're even slower. So what we really want instead is to have a BFT system that gives us low latency all the time, not just in the absence of faults. The system that we designed to achieve this goal we call IGOR, and there are two main ideas behind IGOR. The first is to take advantage of the increasing prevalence of multi-core processors in embedded systems. Increasingly, we're seeing avionics boxes with 8 or even 16 cores. The second main idea is that speculation does not need to be predictive. Instead, speculation can be done in an eager way, where each replica executes on data from multiple sensors simultaneously. That way, replicas don't need to roll back and re-execute because they selected the wrong sensor value. We show that by combining these two ideas together, it's possible for IGOR to get close to or even match the latency of non-replicated systems. Now that we understand the main idea, let's walk through an example of how IGOR works. The system model for IGOR looks just like a traditional SMR system, except now when each replica receives a value from a sensor, they're going to start speculatively computing on that value right away. So if a replica receives values from 3 different sensors, they're going to perform 3 different speculative computations, each on a different core, and produce 3 different states. We refer to these states as temporary states because the replicas still don't know which one will become the final state of the system. While these speculative computations are underway, the replicas execute an agreement protocol, and the purpose of this protocol is to agree on both the contents of the sensor data that they received, as well as the result of the source selection process, so which value is going to be chosen as the trusted input, which again in the simplest case can just be a mid-value selection. Once this agreement process, as well as the speculative computations are complete, the replicas know which value was chosen by the source selection. So each replica that executed on that chosen value then commits the resulting state. That is the final state of the system. The states resulting from computing on any other sensor value that weren't selected are then discarded. Next, all replicas that committed the state send an output to the actuators, and the actuators use a majority vote to mask faulty replicas. So unlike a traditional SMR system, IGOR is able to generate an output even though all non-faulty replicas don't yet have the same matching state as one another. Lastly, replicas that have the state need to distribute it to replicas that don't have it. That way, all replicas have the same matching state before the next execution of IGOR starts. Replicas that need the state can then determine it by majority voting the states that they receive. Now importantly, this state dispersal process happens simultaneously with delivering results to the actuators, so it doesn't actually contribute to IGOR's end-to-end latency. So in a nutshell, IGOR reduces latency through a combination of eager speculative computations and this parallel agreement process. However, we face 2 significant challenges with making IGOR work in practice. The first challenge is that IGOR needs to make sure that the sensor value it selects during the source selection process was actually executed on by enough non-faulty replicas. Otherwise, there may not be enough non-faulty replicas with the same matching state, and it may be impossible to outvote the faulty replicas when sending results to the actuators. For example, consider what would happen if the agreement and source selection process selected 5 as the trusted input in our previous example. Only one non-faulty replica actually executed on 5, so only one non-faulty replica would have the final state, but that's obviously not enough to outvote the faulty replica. What we need instead is to ensure that a value cannot be selected unless it was executed on by at least f+1 non-faulty replicas, where f is the max number of faulty replicas in the system. Unfortunately, existing agreement protocols can't guarantee this property for us. Even though they ensure all replicas will agree on the sensor values, they make no guarantees about how many replicas started with each sensor value. So to solve this problem, we developed a new agreement protocol for IGOR that allows replicas to simultaneously agree on both the sensor values that they received and how many replicas started with those values. And importantly, it does this without requiring any extra rounds of communication compared to a regular agreement protocol. I don't have much time to go into the details here, but if you're interested in learning more about the agreement process, you'll find many more details and all of the relevant proofs in the paper. The second challenge that we faced with IGOR is that even though we parallelize agreement and execution, the agreement process can still take so long when tolerating multiple faults that IGOR can still actually be slow in practice. The reason is that agreement protocols, including those used in IGOR, often require replicas to send increasingly larger messages in each round of communication, and the number of rounds that you need grows linearly with the number of faults you need to tolerate. For example, agreeing on 250 byte sensor data in a typical 2-fault tolerant BFT system, so 5 sensors, 7 replicas, requires replicas to broadcast 45,000 bytes in the last round of the agreement protocol. Those huge messages then need to be fragmented to fit the MTU size of the network. So in Ethernet, which has a max payload size of 1500 bytes, that 45,000 byte message would need to be split into 30 different frames. However, deterministic networks that are used in BFT systems typically require a minimum separation between adjacent frames sent from the same node, and that's to limit contention for switch resources and mitigate the effect of babbling devices. For example, the AFDX networks used in aircraft and spacecraft require a minimum separation of 1 millisecond. So that means that just sending this 45,000 byte message in a single round of the agreement protocol on its own can take approximately 30 milliseconds in the best case. So it really inflates the time that it takes to run the agreement protocol altogether. To fix this problem, IGOR uses a filtering stage before the agreement protocol is executed. The filtering stage consists of one round of communication where the replicas echo the sensor values that they receive to one another. Replicas then only keep a sensor's value if at least two f+1 replicas stated that they received the same value. The end result is that no two non-faulty replicas can choose to keep different values from the same sensor. That means that instead of running our agreement protocol on the sensor value itself, we can run it on only a single bit. Either you have the value from that sensor or you don't have the value. So in the two-fault tolerant BFT example from before, we can reduce the size of messages sent in the last round from 45,000 bytes down to only 23 bytes, which obviously doesn't require any fragmentation. So ultimately, it's a trade-off where by adding one extra round up front in the form of this filtering stage, we can make the agreement process take way less time overall when tolerating multiple faults. Now that we've looked at the design of IGOR, let's see how it actually performs in practice. There were 5 key questions that we wanted to answer in our evaluation. For the sake of time, I'm only going to discuss 3 of them. How effective is IGOR at reducing latency? How much can IGOR improve schedulability? And how does IGOR perform in a real spaceflight application? To answer these questions, we implemented IGOR in NASA's Core Flight System, which is an open source flight software framework used in a variety of real spacecraft. We then ran it on a cluster of Raspberry Pi single board computers. For comparison, we also implemented 3 other systems. The first, which we denote OM, is an agree-execute BFT system based on Lamport's oral messages algorithm. We chose OM specifically because it's used extensively in practice and because it matches the theoretical lower bound for number of rounds to reach agreement, so it's very fast when tolerating single faults. The second protocol we implemented we denote TC, which is based on Turpin and Cohn's reduction-based Byzantine agreement protocol, and that's the fastest protocol we know of in practice for tolerating more than one fault. Finally, we implemented NoRep, which is a non-replicated, non-fault tolerant system that represents the theoretical minimum latency that can be achieved. Our first question was, how effective is IGOR at reducing latency? In these plots, we vary the execution time on the x-axis, which is the amount of time taken by the replicas to compute on the sensor data, and on the y-axis, we're showing the end-to-end latency from sensors to actuators. We can see that compared to OM and TC, IGOR significantly reduces latency, up to 1.75 times in the f=2 configuration. Also, for large enough execution times, IGOR actually achieves the theoretical minimum latency, so it matches the latency of a non-replicated system. Our next question was, if we use IGOR for tasks that cannot meet deadlines using the best existing protocol, how much can we improve schedulability? On the x-axis, we're varying the core workload utilization from 0.1 to 1 for a system with 3 cores. We then randomly generate task sets based on parameters from real systems and show the fraction of schedulable task sets on the y-axis. Our results show that if IGOR is used for tasks that cannot meet deadlines, then we can significantly increase schedulability. In the single fault tolerant case, we can schedule 1.88 times more task sets, and in the 2-fault tolerant case, we can schedule 3.22 times more task sets. Lastly, we wanted to evaluate how IGOR would perform in a real spaceflight application that needs low latency BFT. For this, we chose NASA's Ascent Abort 2 mission, which was a test of the abort system for NASA's Orion spacecraft that flew in 2019. We ported simulated guidance, navigation, and control software from that mission to our Raspberry Pi cluster, and then we compared the execution times of different stages of each of the various BFT protocols. These plots show our results. The x-axis shows time slots in a cyclic schedule, and the solid colored blocks means that a given task was running in that time slot. You can see that compared to the non-replicated case, using OM results in significantly higher latency. It was actually so much higher that one execution of OM would slightly overlap the next execution of OM, which causes a big decrease in control performance and actually causes the rocket to rock back and forth as it's flying, which is definitely not supposed to happen. In contrast, IGOR matches the latency of the non-replicated system, so it doesn't result in any degraded control performance. So in conclusion, we've introduced IGOR, which is a new approach for building BFT embedded systems by eagerly executing on data from redundant sensors. And we showed that IGOR can significantly reduce latency and increase overall schedulability. We also showed that in a real spaceflight application that needs low latency BFT, IGOR was able to achieve the minimal possible latency. If you're interested in learning more about IGOR, or maybe improving it for your own projects, our artifacts and implementation code are available at the link that's provided on the slide, and we encourage you to check them out. Thank you.